So the fluctuation spectrum is motivated by inflation. Okay? And what the fluctuation spectrum is one where you set up fluctuations on all scales, not on any one given scale, but on all scales. And those fluctuations are amplified by gravity. And we have evidence, we've been gathering evidence for this amplification of fluctuations from about 400,000 years back when we see the surface of last scattering in the cosmic microwave background observations. And then as we move to the present day, we have access to galaxies that have formed, the first stars that formed, and the early galaxies that assembled, all the way down to today when we think the age of the universe is about 13.7 billion years. And we now have, for our local universe, for the nearby universe, and going out to even when the universe was about 8 to 9 billion years old, we have enough understanding of the statistics of galaxies. Okay? So I want you to note here, so what we have in the initial conditions, fluctuations in the dark matter. One of the observations that we have are fluctuations in the spatial distribution of galaxies. As you can see immediately, everything hinges on how we relate the dark matter to the galaxies. Okay? And that is not very well understood. And that is where simulations, so simulations, as I said, gravity, the fact that gravity is the main driver for these fluctuations is useful and interesting and allows us to do the simulations. However, in order to match the simulations with any observations, further assumptions have to be made about the relationship of mass to light. There is only one set of observations that does not entail making any further assumption about the relationship between mass and light, and that derives from gravitational lensing. That's the area I work in, so I will talk about that at the end. So there's only one set of observations where we can actually compare simulations and observations without invoking, without an ansatz about how light and mass are related. And so it's very, very powerful. That's one of the most powerful tests that we have of these models at the moment. But I'll come to that in the end. So there's some, there's such beautiful slides that, I just sort of vultured them from the web. I didn't make these, right? So these are all from the WMAP team. So this again gives you a sense of the expanding universe and gives you some idea of the timeline. We think that there's an epoch, that identifiable epoch in terms of thermodynamic conditions, density, temperature, where we think the first stars formed, and then progressively galaxies assembled, and planets, planetary systems, blah blah blah, and us, where we are. Okay. And as I said, there are of course all these interesting. Most of you know all the interesting questions, philosophical questions that arise here, right? What's going on? Quantum fluctuations. What is that theory? How many multiverses, universe, etc. But I think there's a rich set of philosophical issues that arise from just this epoch. And I am much more comfortable working in this epoch because there are tangible observations. Okay, it's a personal taste issue. So just to remind you all a little bit about the scales and the range from which observations are accessible to us today of the universe. So independent of whether the universe, I don't care if the universe is finite or infinite. Okay? As far as I am concerned, there is a finite observable universe, and that horizon, that observable horizon, is a consequence of the finite speed of light and the finite age of the universe. So there is a loss scattering surface out to which we can actually detect photons, and we have. And in the future, a billion years later, of course, this horizon is going to be extended further out. But that's not what I'm interested in is the observational data we can collect today. And where do they come from? Okay? So they come from this last scattering surface, where basically, essentially what you're seeing is a recombination of electrons and protons, fundamental physics signatures that we understand very well. And basically what we have is a uniform background. So all the evidence, the data that we have suggests that we started out from a very hot, dense beginning. And the universe has been diluting, partly cooling and diluting because of the expansion, and that various astrophysical processes that require certain conditions of density and temperature therefore progressively occur in this timeline. And that is pretty well mapped out, okay? Because we assume that the physics that we know and understand is pertinent and relevant at earlier epochs in the universe, right? So there's that assumption. But that doesn't seem like such a wild assumption. So the interesting thing about the formation of structure is that there's a hierarchy of structures over a vast range of scales. You have a lot of galaxies. These are basically, in terms, when I say hierarchy, it's a hierarchy in mass, and it's also therefore a hierarchy in the time during which they form. So the most massive objects in the universe form most recently. The tiniest objects form quite early on. Massive objects typically assemble from the mergers of earlier formed objects. So that's the current paradigm. And you'll see when I show you the simulation movie that if you saw that movie, that's the paradigm you would have too. And so, so there's a whole richness of structure that is formed, the observable, nearby observable universe as well as. So the one other key thing I want to point out is underlying our understanding of how fluctuations are generated and are propagated is the assumption of a cosmological principle, that the universe is by and large, on very large scales, isotropic and homogeneous. It turns out it is globally, but the nearby universe is quite clumpy, and in fact the not so nearby universe is also fairly clumpy. However, this assumption is sacrosanct, and I think that that's another place, because we can't calculate. We can't calculate a theory if you don't make that assumption. Okay, so we're stuck there. Okay, let's quickly move on. So you must have all seen this very beautiful map. So what is this? Our temperature fluctuations on the sky, where actually the temperature is uniform in any two locations on the sky, even regions that might not appear to have been causally connected today, but due to inflation at very earlier times, they were causally connected. So what has been removed here? So it's a uniform black body to 1 part in 10 to the 5. Okay, so that piece has been removed. I'll just show it to you later. It's basically, this whole thing should be one green shade. What has been amplified here are the 1 part in 10 to the 5 fluctuations, where you have the blue spots, which are colder spots. So this is a map of temperature. Okay? And so the hot spots are these little red blips, but these are very, very tiny deviations. But there's a lot of information in these deviations. Why? Because these deviations imprint everything that the photons have encountered on their way to us from the surface of last scattering. So basically, if you look here, photons have been coming to us from this last scattering surface, and all the structure that I'm talking about in the nearby universe has assembled, is evolving here. So these photons are encountering all the structure, and the imprint of this structure, and note right now structure is all dark matter structure, is what you see imprinted there. Okay? So there's a wealth of information, there's a wealth of statistical information in this map, okay, that has been very ably exploited. So exactly, so this is exactly what I wanted to show you. In fact, the temperature of any 2 points of the entire sky, right, so this is sky folded out, is uniform, extremely uniform, and the fluctuations are at the very, very small level, 1 part in 10 to the 5. And so what's been removed here, so this is just a map where this has been removed, the smooth components, the deviations have been amplified, and here we've actually left in our galaxy. So our galaxy is very, very dusty, and it sort of shows up here with this sort of red cloud. But we understand quite well how to analyze these fluctuations, how to extract information from these fluctuations that can constrain the theory. And I think you must have all seen the version. I just wanted to connect back to, you must have seen motivations for why inflation, which is again a very generic phenomenon, is useful and is needed to understand and interpret observations of the cosmic background radiation. Okay, so let me quickly move on to showing exactly what the observations show us and what simulations simulate, and how we're going to make that correspondence. So just to show you very quickly, so this is the first slice. I like this one because it was the first ever redshift slice. So this is time or distance, if you will, and that corresponds to a recession velocity away from us, and that's what is marked here. So an object here is receding away from us at 5,000 kilometers a second.